Hello, Bobcats. Just wanted to go over a couple of details for Charles' law, which is the relationship between volume, which we talked about in another video, and temperature, which of course is the measurement of the motion of the particles, which is related to how hot or cold something is. Okay, a little story for when I was a kid that first experienced Charles's Law. I went to the park. I was going to play football, and my football was a little bit flat, and so I was very upset. And I threw my football into the windshield near the wind in the car near the windshield up on the dashboard there. Went and played at the park for a couple hours. Came back, grabbed my football. Was so surprised. It was pumped up. And I was like, someone broke into my car and pumped my football up. How dare they? Who was this thief? Later on in life, I learned that the thief was Charles's Law. And so you can see this relationship here with this two images of these bottles here, in where we have one bottle has a larger volume, okay, on a nice hot afternoon, not like today, but it's snowing outside in April. And if we compare that to this, putting this water bottle, or this, not water, it's a water bottle full of air, not water, this bottle full of air, put this in the freezer, put it outside over a cold night, and the volume decreases, right, of those gases. So you can see this relationship here would be direct. As the temperature goes up, hot, the volume goes up, okay? So as the temperature rises, right, the volume rises, okay? And this would be a direct relationship. One goes up, the other goes up, okay? A little different than Boyles Law that we looked at with the bottle lab we did before we got out of school. Had this bottle with a syringe in the bottle, and the syringe was 12 milliliters of air. The bottle was full of air. Put the cap on, okay? Then, oops. Here's the, so you can see these blue dots are the air that's in the syringe. The green dots are the air that's in the bottle, right? So we close that. They'd have the same pressure inside the bottle and inside the syringe. Then what we did was we pumped up the bottle, the larger bottle, which increased the amount of moles or gas particles that were in the larger bottle, but because all these green gas particles were bouncing into the syringe, slowly pushed the syringe to a lower volume, right? Same number of blue molecules here. If you want to count them, you sure can. But our volume decreased with this increased pressure on the outside of the bottle. Okay, that was a inverse relationship. And so a relationship between pressure and volume, that relationship, that mathematical relationship is indirect, right? Indirect. Inverse. Another way we can say that mathematically. And so in that case, the way we would write that in an equation would be that they are inversely related, and so one would be the reciprocal, right? So pressure, and so now you can see as this goes up or goes down, the volume goes down, the pressure goes up. They're opposites, right? Inverse opposites. And so that was the Boyles Law. Those are the inverse relationship. For Charles' Law, because it's direct, we can look at this in terms of volume. Now, on that last slide, notice I didn't use an equal sign, right? Because it's proportionate to. To make that equal, what I'd have to do is turn this into a constant. Wouldn't be 1 necessarily. It'd be some constant. In which case, then I would be able to not use this proportionality symbol, but you actually use an equal, so that pressure is equal to this constant times or divided by volume. And then what we did was, this is what we did for using Boyle's Law, was we multiplied both sides by volume, right, which gives us equal to this constant. Or what we were doing is easier to do, is not use this constant yet, but say Well, if we had some first variables, we could change those to some second set of variables that are related to each other. And so if you can measure if one goes up, the other one will go down. Okay, and we can use this equation here for a Boyles law, right? If you remember doing that on the last homework problems we were doing. So with a direct relationship, we have proportionality as this goes up, the temperature goes up, or vice versa. And so if we can say we can take this and multiply it by some constant, then we can change this proportionality instead of a proportionality into an equal sign, right? And then if we divide both sides by temperature now, you can see that, cancel here, that now we can do the same thing where we can set some first set of variables, and that being equal to, instead of a constant, I'm not going to use that yet, instead of that we'd have some second set of variables. And so you can see directly related is this is a V1 divided by T1 equals V2 divided by T2. And so that's Charles's law in equation form that you'll be using on those problems. Now, what this does, though, is this brings up a very interesting point. If you notice, we're dividing by T. And so a lot of times in our everyday lives, we like to use either Celsius or centigrade, right? Or we like to use Fahrenheit. However you spell that. Fahrenheit based off of human body temperature, about being 100. Celsius based off of phase changes of water. 0 degrees being freezing point and 100 being boiling point at sea level. I'd like to learn more about those. And so think about this. If we're using Celsius and Fahrenheit, there's a point where we have 0 degrees Celsius, right? Or negative. And the same thing goes with Fahrenheit. You have 0 degrees or negative. And so if we just think about this mathematically for a second, because science and math go hand in hand, if we're dividing by a 0, right, what's going to happen to our relationship? We can't measure it. It's undefined, right? If we have this negative value in our temperature, we can't really use it. Okay, and so this is why we cannot use, for these Charles law problems, we cannot use Celsius or Fahrenheit. In fact, this is why scientists, mathematicians, came up with this other unit that we use. It's called, it's on an absolute scale, and it's based off of the Kelvin scale. Okay, and the whole reason it's used and invented was because we can't mathematically look at these relationships when we have something like 0. We can't divide by 0. And it changes when we have this scale that goes into a negative. So we have this absolute scale that we use that's called Kelvin. Okay? And so it goes from 0 Kelvin, which is 0K, it's capital K, right, is what's called absolute 0, when all motion, because remember temperature is motion, all motion stops. We've never been able to reach that before. We've been within a billionth of Kelvin of it, but we've never been able to reach this scientifically. All motion stops. Even the electrons moving around the nucleus of the atoms will stop. This is what it's based off of, right? So there is no 0, there is no negative. Now we can use this equation. So to do these problems, you cannot do it without being in the unit of Kelvin. Every problem has to be converted to Kelvin. Okay, how do you do that? It's pretty easy. It's based off Celsius. They are on the same scale. If you go up by 1 Kelvin, you go up by 1 Celsius. Okay, this is on your equation sheet, of course. But if you want to convert from Celsius to Kelvin, all you do simply is add 273.2. I think on the equation sheets it's 273.15. You can use either one. Okay, so if you have something like 21.2 degrees Celsius and you want to change that to Kelvin, you just add 273.2, and that will give you Kelvin. So that'd be what, 284 Kelvin, and there's no degree sign on Kelvin. Okay, If you're going from Kelvin to Celsius, then you would just subtract. So it's on the same scale, but different part of it. Okay, and so you must change it to Kelvin. Hey Bob Cats, just finish up this video. I'm going to move to my kitchen, a little demonstration that you can do. I'm not going to finish it today. I'm not going to perform it today. I would like you to try it first. Maybe I'll show you my results later on in the week. What you'll need for this is a set of tongs from your kitchen. You'll need a aluminum can. Just any aluminum can that you can find will work. And you'll need a bowl of ice cold water. Okay. And of course your stove. Now, you can use a funnel. You don't have to use a funnel. You can just put this under the sink where you're going to use. My kitchen is a mess. Just a little bottom of the aluminum can full of water. Okay, you're going to take the tongs. You can use oven mitts as well. Turn this on nice and high here. I'm going to put without burning myself, put my ice water nice and close by here. Spill a little bit of that water first. You have to practice with your tongs. Make sure you can get a good grip. Let me use these other ones. Okay. And what you're gonna do is you're gonna put it over the flame here, nice and hot, and let it sit there until you can see a little bit of steam rising out of the mouth hole there. Okay. You might be able to hear it starting to boil. Okay, just be careful when you're doing this. Don't burn yourself. What you're going to do now is put your ice here. You're going to take your tongs. Once you start to see, it might take a couple minutes here to see some steam coming out of the top of the can. But what you're going to do is you're going to get a nice tight grip. You can hear it starting to boil there. Okay, and what you're going to do, get it close. Once you get nice and hot, with the steam coming out of there. What you're going to do is you're going to flip it upside down as fast as you can. Try not to let too much of that water spill out. Upside down and with a hole beneath the surface of the water. Okay? And see what happens. See how Boyles Law takes over. Try that on your own and I'll show you my results next time.